Okay, today we're going to look at the four-quadrant model of jet streaks. You've heard us mentioned several times in the class. When I say us, I mean Instructor Davies and myself have talked to you about the fact that upward vertical motion is favored in the right entrance and the left exit of a jet streak. And we're going to go through the math behind that today. So this is the long version. Before it was just we told you, and now we're going to show you why that actually happens. So in order to do that, we're going to start with a proof that's actually done in your book, and we're going to start with the equation on page 79, and this is actually in chapter 4 of your book, which is titled Applications of the Equations of Motion. So what do we have here? We have an equation for geostrophic wind, and that equation is equal to 1 over f in the k-hat direction cross the gradient of geopotential height. The del p here depiction, or at least the del sub p, means that we're talking about the gradient on a constant pressure surface, or an isobaric surface. So this is the vector form of the geostrophic wind on an isobaric surface. If you want to take a look at it, you can go to your text. The derivation actually precedes this in the text. And in the equation, F is what you'd expect, Coriolis. Del P, again, is the gradient on a constant pressure surface. And I believe this is phi is geopotential height, which is equal to gravity times height, or z. So let's actually do the math here. So we do the cross product, and what do we end up with? Well, we have negative 1 over f d phi dy, I think, theta phi, yeah. And 1 over f d phi dx in the j-hat direction. And that's what this is right down here. This is the... I'm not sure if you're seeing my cursor, so I'm going to circle it with a green highlighter. So this is what you end up with right here. And, oh, by the way, this is where we started when we calculated the geostrophic relative vorticity equation in terms of geopotential height. So this is your equation. This is your U sub g, and this is your V sub g. So let's actually go down and calculate the horizontal divergence of the geostrophic wind. And oh, by the way, that's what this section was all about. It's to prove that the geostrophic wind does not actually diverge, or divergence is equal to 0. And it makes sense when you think about it, since geostrophic wind is always parallel to contours. It never actually crosses contours, so therefore it's neither diverging or converging if it's staying parallel to the the contours at all times. So let's actually do del dot v sub g, or del dot the divergence of the geostrophic wind, and we have the del defined over here, and we end up with negative 1 over f, the second derivative of phi with respect to xy, plus 1 over f, the second derivative of phi with respect to y and x. What does that equal? That equals 0. And that means that the geostrophic wind is non-divergent. Okay, so that's step 1. Just remember that. Geostrophic wind is non-divergent. And we'll hit it again soon. So step number 2. Now let's write the continuity equation in isobaric coordinates also. So in order to do that, we again turn to our text, and this is starting from page 81 in your text. Kind of goes through this derivation also, but I'm going to step you through. If you just want some backup, you can go to the text. So we got our differential volume, which is just dx times dy times dz. But then we can go plug in from the hydrostatic equation. We know the hydrostatic equation is dp dz equals negative rho g. We can rearrange that to write in terms of dz, and then plug back into the differential volume equation. And what do you end up with? You end up with equation number 1, which is right here. Differential volume is equal to negative dx times dy times dp divided by rho g. Now that we have that equation for volume, we're going to take a look at the differential mass of the control volume. So the differential mass is just simply the density times the volume, and then you would get the mass. So we sub in number 1 from above. So here's number 1 again. So that comes down here. And then we end up with the differential mass is equal to negative dx dy dp over g, because the rows cancel each other out. So the row up here times the row down here cancels out. So we end up with number 2. Then we take a look at the differential mass from a Lagrangian perspective, i.e. following the parcel. Conservation of mass tells us that the parcel cannot gain or lose mass. So the change in mass per unit mass, so this is, we're making this as specific variable. So the change in mass per unit mass, how do we do that? Well, we divide by the differential mass, and then we take a look at the change in the mass with time. We know that if we have to conserve mass, that change in mass with time will be equal to 0. So now we stick 2 in for the differential mass into this equation. So here's number 2. So we bring this equation down over here, and we actually plug and chug. This is just simply going through the motions. So we can notice that there was a negative up here. So this was negative g. This is 1 over differential mass. Negative g dx dy dp. Then d dt of, again, differential mass, which again was negative, which is negative dx dy dp over g. But because this is a negative inside, a negative outside, they can both become positives, hence the reason you see the positive, and the g's cancel each other out. So what are you left with? You're left with 1 over dx dy dp times, when we do the chain rule, we have d differential of x with respect to t, and then multiplied by dy dp. Then we have plus d dy dt dx d times dp plus d dp dt dx dy equals 0. So we move on to the next page and continue this. So let's start, reducing things down. So if I multiply this through this right here, we see the like operators up here. If we multiply it through, what we end up with is just d dx dt 1 over dx, d dy dt 1 over dy, d dp dt 1 over dp equals 0. Now let's take a look at what we're actually looking at. What is dx dt? That's u. So we're looking at the change in u. This is the change in v. This is the change in omega. Omega is a term that you haven't seen before, or perhaps we've talked about it previously, but we're going to talk about it a whole lot more later in the class. But u and v are what we'd normally look at, but omega, by definition, is change in pressure with time. Note that because pressure decreases with height, if pressure is decreasing with time, that means we have upward vertical motion. So omega is negative for upward vertical motion. So remember that when we keep going forward. So now we plug what we determined into the equation above, and we end up with the continuity equation in isobaric coordinates. And I've labeled this number 3. So let's keep on moving. So if we rearrange this thing, what we're going to find is that we have du dx plus dv dy equals negative d omega dp. Well, what does this equal? This is, by definition, the divergence of the horizontal wind. So, interpretation of this equation now. The horizontal divergence is directly related to vertical motion. Vertical motion being the d omega piece of this. So if we know the horizontal divergence, or how horizontal divergence varies in a column at various pressure levels, then we can determine the vertical motion in the column. And I'll take you through a hypothetical example. We know that at a surface low we've got convergence, and then we have aloft a divergence, and that provides us with some upward vertical motion. So we know what the answer is prior, but let's take a look at it mathematically. So if we have convergence at the surface, the divergence would be negative. If we have divergence aloft, the divergence would be positive. So from number 4 above, which is, here's number 4, we have, if we go from P aloft, P surface P aloft, P surface P aloft, how does omega change between these two pressure levels if the divergence goes from negative at the surface to positive aloft? So let's take a look at it. Here's divergence aloft minus divergence at the surface equals negative omega aloft minus omega at the surface. Now let's take a look at a fact, and this drawing is what we're trying to show here. At the surface of the Earth, there is no source of air from below. So we're stating the fact that at the surface where air is converging, there is no vertical component of wind. A small distance above the surface, like right up here, there would be vertical motion, but at the surface, right where it's meeting at the surface, there is no vertical motion because there is no source of air from below. So what does that allow us to do when we've got this equation above? We know that the divergence aloft is positive, so we have a positive, minus, we know that the divergence at the surface is negative, minus a negative, and I have no idea what that circle is. I don't think that was in my notes, but oh well. So we've got a positive minus a negative, so that turns out to be a positive, equals negative omega aloft. And we got rid of the omega at the surface because that went to 0. So since we have a positive over here equals a negative times whatever's inside the parentheses, that means omega p aloft, or omega at the upper level, must be negative, and therefore we have upward vertical motion. Why? Because omega equals dp dt, and dp must be decreasing to be negative. So there is upward vertical motion. Realize that in the upper levels, this can be any upper level where there is divergence. You can have divergence at 500 millibars. You can have even more divergence at 300 millibars. It just means that you have upward vertical motion through 500 millibars heading up to 300 millibars. At some point, you're going to reach the top of the troposphere, and you're going to end up with divergence, and your vertical motion is going to go to 0. And that's what provides you with, again, horizontal winds aloft. So now let's take a look at what we've learned so far, and this is moving along rather quickly, and it's going to take a whole lot more time in class to go through this. So what have we learned? From part 1, we know that the geostrophic wind is non-divergent, or del dot v sub g is 0. So from 2, divergence of the horizontal wind is directly related to vertical motion. Now, break the horizontal wind into two components. We've got the horizontal wind that we can observe. We know that at least a portion of it is geostrophic, and then anything that isn't geostrophic is called ageostrophic. So we know that the total wind is a combination of these two, where Vg is geostrophic wind and Vag is ageostrophic wind. Now let's re-examine equation number 4 from section number 2. So let's go up here. Here's number 4 from section number 2. So let's scroll back down. If I plug in for the horizontal wind Vg plus Vag, I end up with negative d omega dp equals del dot geostrophic wind plus ageostrophic wind. If I multiply that through, what I end up with is the divergence of the geostrophic wind plus the divergence of the ageostrophic wind. But we know from section 1 that geostrophic wind is non-divergent. So that is equal to 0. It goes away. So what does that mean? Right here's our equation, my friends. Negative d omega dp equals the divergence of the ageostrophic wind. This is a pretty big statement. What it is saying is that the convergence and divergence of the ageostrophic wind determines where vertical motion will occur in the atmosphere. Yet we observe that the atmospheric motions are largely geostrophic, or nearly geostrophic. So if we can identify areas where we have convergence and divergence of a geostrophic wind, we can tell you where the vertical motion is going to be. There are going to be many different ways of figuring out where vertical motion is going to occur, but the reality is they're all backdoor ways of finding where the winds are ageostrophic and you have convergence and divergence thereof. So, how does this relate to jet streaks? Well, going back to page 79 of Martin, we're going to start with the vector form of the horizontal equation of motion in isobaric coordinates. And I believe it's the horizontal frictionless version also, so there's no friction in this equation. So we end up with acceleration, or this is from the momentum equation, so acceleration equals negative gradient of height minus f in the k hat direction cross the wind. So v is the wind velocity, f is Coriolis, and phi again is geopotential height. So we rearrange and take the vertical cross product and divide by f. What does that mean? It means I just go k hat over f cross both sides of this equation. So I rearranged it a little bit. I realized that I stopped using my pen and started using my mouse, which is why it's probably messy, but I take this portion here, bracket that portion off, send it down there, and multiply by 8. And I take the cross product, k hat over f cross product that portion, and then I move this piece. That was not good. Control Z. Oh, that's not good either. I'm going to scroll back down and try it. Hopefully that didn't screw things up too badly. It didn't. So I take this negative del phi, move it over here, and again do the k hat over f cross that particular portion of the equation. And what do you end up with? Well, from 1, the original equation we started with, and I lost my highlighter. From section 1 originally, what do we have? And don't look because I'm going to scroll up, and it's hopefully not going to make you dizzy. This is the original equation we started with, right here. So scrolling back down, we know that that is the geostrophic wind. Now let's examine this piece right here. Notice we have minus f over f. You can bring that out since it's a constant, so this can come out over here. So we end up with minus 1 k hat cross, in parentheses, k hat cross v. If we examine this closely, we will see that by the right-hand rule, k cross v gives you a vector orthogonal to both. And then if you do k cross that resultant vector, what you end up with is a vector the same as the original in the opposite direction. So you're 180 out, so you end up with minus v. And you can think through that. Now, if you want to think through it closely, just sub in an arbitrary vector in the I hat direction in for v. So make this I hat. So k cross I. So if I k and I cross I, then I'll end up a vector in the j direction. Now I've got a j vector, so I've got k cross j. So now k cross j will end up giving you a vector in the negative I direction. So go through the motions there and you'll be able to figure out that this is correct. You end up with negative v. So I stick in negative v over here. Notice I haven't done anything to the left-hand side. So I've got negative v, because I had the negative 1 outside, turns into v. So v minus vg. And from number 5 above, number 5 being, I'll try to scroll slowly, right here, number 5, we saw that the wind is a combination of geostrophic and ageostrophic. So if I take the wind minus Vg, or geostrophic wind, then that equals the ageostrophic wind. So down here we have an equation. K hat over F is equal to, and again realize that I'm not using my pen for some reason, but you'll still get the point. So k hat over f is just a constant value vector in the k direction. dv dt is exactly what you think that would be. The change in velocity with time is acceleration, and VAG is ageostrophic wind. Now for the payoff. Here's a drawing of a jet streak. I've got a lot of information here, and I'll step through it in time. But notice that the center is 120 knots, here's 100 knots, here's 80 knots. This is my x direction right here, left to right, y direction, north and south. So, I'm calling this the entrance down here at this end. So this is the right entrance, left entrance, left exit, right exit. The winds are going in this direction through the jet streak. So here's my wind. And you always stand at the entrance looking down through the jet streak to determine left and right. So if I'm standing right here looking in this direction, this is my left, this is my right, right, left. This half of the jet streak is the entrance, this half of the jet streak is the exit. So let's look at what happens with the equation. So I should have rewritten the equation, and I might do that now. I'll try to write it here and see if we can keep it in sight. So k hat over f cross dv dt equals VAG. So if I keep that equation in mind, and perhaps I'll need to move it around if I can, I don't even know. But dv dt. So we know that if you're at point 1, which is that point right there, that's not what I want to do. Let's color here. I need a thicker marker. I don't have a thicker marker, so I'm going to highlight it. Here's point 1, here's point 2. If I'm at point 1, we know that the velocity here is less than the velocity here, so that means I'm accelerating in this direction in the entrance portion of the jet streak. So that means it's in the positive I direction. So acceleration, which is right here, is in the positive I direction. If we have positive k, which is 1 over f, that's going to be positive because you're in the northern hemisphere, cross a positive I, because dv dt is in the positive I direction. By the right-hand rule, we end up with a positive j. What does that mean? Ageostrophic wind is going to be in the positive j direction, so from south to north. Now let's scroll down a little bit. And again, always keep in mind that equation up top. It's going to stay the same. So by inspection, if we take a look at the acceleration out here on the edge of the jet streak from, say, this point to this point, you're obviously not increasing in speed as much. So the greatest acceleration is in the center line of the jet. The magnitude of the ageostrophic wind is proportional to the magnitude of the acceleration. And the ageostrophic wind away from the center line would have a lesser magnitude than in the center line, but in the same direction. So what does that mean? It means looking downstream, as in looking in the direction of this arrow right here, that, and I'm going to talk through it and then go down and look at the words, is that we end up with ageostrophic wind that is a higher magnitude in the center and lesser magnitude away in both the entrance and the in both sides of the entrance, so the right and the left. So in this case, I've got higher speeds going to slower speeds. So this car, if these were cars driving, would run into the back of this car. That is convergence. If we have convergence, then we have downward motion. Now look at it down here in the right entrance. This is slower, this is faster, so this car is running away from this car. So that means we have divergence here, and divergence supports upward vertical motion from below. Similar inspection, left exit. This time we end up with an acceleration in the negative I direction. If dv dt is negative I and we have positive k, negative I, we end up with a negative ageostrophic wind in the j direction. So we end up with this wind right here, going from north to south. Sorry about the issues talking, but it's getting pretty late at night and I need to get home. So we end up with convergence in the right exit, and we end up with divergence in the left exit. So we have support for upward vertical motion here and here, and we have support for downward vertical motion where there's convergence here and here. This is why we've said there's support for upward vertical motion and deepening of lows underneath the left exit of a jet streak or the right entrance. So it's another thing that can add to upward vertical motion, can add to stretching of the surface vorticity, can add to the spin up of a surface low. So it's just another piece of the puzzle. When you stack all these things on top of each other, you can end up with development of an extratropical cyclone and or weather. There are also times where you don't need an extratropical cyclone at the surface. This can help support upward vertical motion and potentially rain even where you don't necessarily have a surface low or a fully developed extratropical cyclone. So we've already talked about this, but looking downstream, right entrance, we've got divergence, upward vertical motion. Left entrance, we've got convergence, downward motion. If we move to point 2, which is over there on the exit side, we see that we have right exit converging and left exit diverging, again supporting downward where you have convergence and upward where you have divergence. That's pretty much it. I'm guessing that this will actually take us 2 to 3 classes to actually get through in class. So luckily you can actually pause this video. It should be the same exact notes. I'm going to write everything you see on the boards. I'm also going to give you some objectives in class that you didn't see here. And that's it for now, and I will talk to you later.